Hello, it's Valentine from Simplistic, and today we're going to take a look at a problem where we're going to solve for the H3O plus ion concentration for a 0.250 molar hydrofluoric acid solution. So first of all, hydrofluoric acid is a weak acid, and that means that this molarity is not going to be the amount of H3O plus ions that is going to be generated. We cannot make that assumption. We have to create an ice table, okay, initial change equilibrium table to figure out, and then we have to use the Ka value for hydrofluoric acid to figure out the H2 plus ion concentration. All right, so I'm gonna, on the right hand side out here, I'm gonna write down the value of Ka for hydrofluoric acid, which is, and you can get this from a table, 6.8 times 10 to the negative 4. That is the value of Ka for hydrofluoric acid. All right, the next thing I'm going to do is I'm going to create an ice table for the ionization of hydrofluoric acid. So we write HF, aqueous, ionizes to form H plus aqueous plus A minus aqueous. All right, so what we're going to do is we're going to write initial I, change E, and equilibrium, change C and equilibrium E. So initially we have, first of all, this problem I just want to mention out here. This shouldn't be 0.25, that is a mistake. It should be 0. I'll write it up here. It should be 0.500 molar, okay? All right, so once we got that out of the way, so we have an initial concentration of 0.500. In the beginning, nothing happens, so you have 0 and 0 of H plus and A minus. The change is going to be, let's say the hydrofluoric acid ionizes by minus X. So, and then we have X of H plus and X of A minus. And then at equilibrium, we're going to have 0.500 minus X for HF. We're going to have X for H plus and X for A minus. So the equilibrium expression for this is going to be Ka is equal to H plus, concentration of H plus times concentration of A minus over the concentration of HF, which is equal to X square over 0.500 minus X. And K, so let's go ahead and take the value of Ka that we got from a table and put that in here. So 6.8 times 10 to the negative 4 is equal to X square over 0.500 minus X. So at this point in time, we actually have a quadratic equation in X square if we keep this X down here. So we're going to make an approximation, which we'll test later on in the problem, where we'll assume that this X out here is so small, it's so much smaller than 0.500, that if we subtract the X from the 0.500, for all intents and purposes, we're going to be left with the same quantity. So we're going to just go ahead and scratch that X out from the bottom, and that'll help us make this problem a lot easier to solve. So once we scratch the X out of the bottom, we're going to essentially multiply both sides with 0.500. So when we do that, we get X squared is equal to 0.00034, and then the square root of that, so X is equal to 0.018 molar. So now we have the solution for X, which is the same as the concentration of H plus, which is the same as the concentration of H3O plus, okay? So the question is this the assumption we made out here to eliminate the X, is that assumption a valid assumption or not? To test that validity of that assumption, I'm going to write that out here in green. The test the validity, we just take the value we got for X and we put it over the value we subtracted it from, and then see if that is if that comes out to be less than or equal to 0.5. So we're testing X over 0.500, and we're going to see if this is it less than 0.05. So it turns out if you take 0.018, which is the value of X we found, and let me just write that properly, and we take it over 0.500, that ends up being 0.036, which indeed is less than 0.05. Therefore, our assumption out here is valid. All right, one last thing to mention before we wrap this up. Uh, when a problem gives you H3O plus ion concentration, notice carefully how I wrote the dissociation, or the ionization of the acid in as an H plus aqueous. This is the same. Let's write that in red out here. This is the same as H3O plus. And the reason for that is, if you kind in green out here on the right hand side, I'll kind of write that out. If you took HF and you reacted it with water, because really aqueous means it's in water, you get H3O plus F minus. Okay, so all we did was, instead of writing the water part out, we put the aqueous sign, and that symbolized the water. And it just helped us not be confused by one additional water molecule on the left hand side when we're writing out the ice table, because then some of us would be thinking, okay, well, what happens to the water? Does that decrease in concentration? And the important thing to realize is that since water is a liquid, its concentration is constant. Sorry, a pure liquid, its concentration is constant. So therefore, it plays no role in the equilibrium expression. I hope that made sense. Thank you for watching.